we have to design at different levels. Even software requirements, we have to first analyze the requirements, and then as we step on to design, we have to design our high level architecture, and then we have to design modules, packages at high levels, and then we have to look at class and component levels, which are further at the lower layers. So we will now discover what are the different issues which we have to take into account when we design at class and component level. As we know, as shown in this slide, class is a programming abstraction which was mainly introduced by object oriented programming languages. So we have this notion of classes and objects. Classes provide us the definition of the structure and the behavior of its instances. So when we say we have a class of a few objects, and whatever is the behavior for the entire class, that is described by the class description. So when we use this term objects, we are mainly referring to instances of the classes, the end instances. So the main concept in the class as an abstraction is separation of interface from the implementation. So we separate the externally observable behavior from its implementation. For example, look at a real life object such as a washing machine. We operate the washing machine using an external interface. So that is the observable interface of that object, and the implementation that actually drives the machine, the logic inside the machine, is hidden. So we have the interface and the implementation. If you look at any real life object such as a data projector or a machine or any other real life object that you see, any manufactured machine, it has a nice interface through which you have to use the machine. If you open the machine and manipulate it directly, some of the interfaces may not be guaranteed because you might have changed the implementation and no more you can guarantee the interface. So that property of enforcing the abstraction of the object, the externally observable behavior through implementation, is called encapsulation. Encapsulation guarantees that the implementation lies hidden inside and it's accessible only via the official interface. Whatever is available to the user to a given role, that interface gives the access to the object. So that interface is exported. So these are the important concepts when we talk of class as an abstraction. So when we have the actual washing machine, that's an object, and the definition of that washing machine is a class. So we have a class of washing machines. In that class we may have many units. So class is a major programming abstraction, and the same can be used in design at design level. You can design systems of classes, and then its implementation can be through an object oriented programming languages. So mostly when you do object oriented software engineering, you come across this term called class. UML has a notation for representing a class and interactions amongst the classes. So you design at the class level, and then when you implement, you convert those classes into programming language classes. So some example classes are given on this slide. For example, class account. When we want to design a class, we have to first think of its interface. That is very important. So design of individual classes means you first think of the abstractions of the classes. Say now we are looking at two examples here. Class account. So its interface is first initialize the account. So when you initialize, what are your initial attributes? What is the state of the account when it is initialized? Then you can operate during the lifetime of the account. You can operate on this object of class account, any object of class account, through this interface. You can invoke methods such as deposit, withdraw. You can check the balance using method balance, or you can close an account. So this is the interface of class account through which the object is accessible to you. And the implementation of the class account, that is the internal details involve data structures or data representations for, say, storing customer details, the actual amount, the balance, etc. That is hidden from the externally observable behavior. You cannot directly manipulate this. You have to invoke the functions, the member functions provided to you by the class description, and any instance of this class will provide you these interfaces. So, instances are objects and classes are descriptions of those objects. Now, there is another class, class list, which has an interface insert and fetch. You can insert into the list and you can fetch an item from the list. You can operate on this list through these member functions. Its implementation could be the local storage, how the list is stored internally, whether it has a static storage or is it dynamically allocated, and so on. The head and the tail pointers, whatever are needed to maintain the state and to make these operations possible on the list. The implementation details are hidden. So, class has implementation and interface. These are the main components, and the guarantee is given by the programming language that the object will be accessible only through the interface. If such a guarantee is given, then you are enforcing abstraction by encapsulation. So, there can be different kinds of classes. When you are thinking of classes, when you are designing your classes, mainly we can classify them into three categories: concrete classes, pure abstract classes, or partially implemented classes. Concrete classes are those which are used directly by instantiation. You will see these in different libraries. You can directly use such a class and instantiate it and invoke methods. So, it's fully implemented class. Or if you want to extend it, you can extend it and possibly override a few member functions in that class. That is also possible through inheritance. But main property is that you will be able to directly instantiate it and access member functions on it. It's completely implemented. One can of course override some of the member functions and specialize the class using inheritance. Second type of classes that you can see is pure abstract classes. These are used as superclasses. They can only be used as superclasses because they are pure abstract. What do we mean by pure abstractness of a class? It means that no member function is completely implemented in the class. In fact, no member function is implemented in the class is even more stronger. The third type of classes is partially implemented class. Now, in this case we have a few member functions which could be implemented. So, we have concrete classes, pure abstract classes where you find no member function implemented. In partially implemented classes we find a few member functions could be implemented and few are left out. They are not implemented in a class. So, the class cannot be instantiated because those member functions are not available. So, when we design classes we can think of these three kinds of classes. Concrete classes directly come forward from the application domain. Pure abstract classes come forward when we want to organize the classes into hierarchies which exhibit common behavior. So, superclass provides you the common abstraction. Partially implemented classes are very useful when you design frameworks. When you design frameworks, you want to design a framework in terms of these partial implementations, so that the actual implementer of an application takes this framework and only provides the subclasses, and a lot of logic is embedded in the framework itself. So, these are the three main applications of these three kinds of classes. The concrete classes mainly used as it is, they are directly available in the real life domain, or you can use them as libraries. The pure abstract classes for capturing the general behavior through inheritance, the common behavior through inheritance, and partially implemented classes are very useful in frameworks. So, we can see that there are three levels of abstraction. You talk of objects which are instances of the classes. Then you talk of classes which defines structure and behavior of a class of objects, a full category of objects. So, that all instances of that class then guarantee whatever behavior that is guaranteed by the class description. And then there are meta classes which are classes of classes. So, if you want to describe class level attributes, for example, you want to keep the count of number of instances of a given class, where are you going to keep that state? Are you going to keep that state in every object? That will be unnecessary redundancy, and then you have to again maintain the consistency. Instead, if you maintain that attribute number of instances of a given class within the class itself, and you can ask the class to give you the number of instances that it has created, then you are talking of behavior of the class itself. You are going to invoke member functions on the class. That means the class is also going to be treated as an object, as an instance. Now of what? Of its own class, which is called meta class. So when we want to model class level attributes, when we want to design something at meta levels, we are talking of class level attributes, then we need this modeling ability called meta classes. So these attributes are at meta level, and the member functions are at meta level. The member functions invoke those attributes. They are described at meta level. They are invoked on classes themselves. So in such a system, classes are treated as instances. Now, not all programming languages provide you this facility of meta classes directly through a notion of meta class, but they give you some alternatives. For example, in C++ and Java, you have static attributes and static member functions. You can invoke those member functions directly on the class. You don't need an instance for it. So those are the class level attributes and class level member functions. In programming language Smalltalk, you have a direct support of meta classes, and you can go on in the meta class hierarchy. So there are meta classes and so on. But languages like C++ and Java take care of some of these meta level attributes through these alternative constructs such as static member functions, static attributes, constructor, and so on. Now we are going to look at an interesting method of designing classes, Beck and Cunningham's CRC method. This was discussed in an Uppsala paper around 10-15 years ago. So what does CRC stand for in this term CRC method for object oriented thinking? First C stands for classes, R stands for responsibilities, and second C stands for collaborators. So we have this template which is shown on this slide. First we describe the class name, then we want to list its responsibilities, what are the responsibilities of this class, and then its collaborators, with which classes this class collaborates. So the responsibilities of a given class are the member functions exported by the class, so that the class carries out the responsibilities via the implementation of those member functions. And in order to complete these responsibilities, who are the other collaborator classes, with which classes does it need to collaborate? Many classes are standalone and you can directly use them without having to connect them to other classes, but in a big system there are collaborations. Via those collaborations, collaborative actions are possible and you can implement a higher level functionality. So the collaborators of a given class also has to be listed. Our recommendation is that in the third section, along with the collaborators, you also list out collaborations. So what are the collaborations? For what responsibilities you need these collaborations? So the collaborators are always the other CRC card. So this is one card, this is called CRC card, and it's a palm top card. You can make a small chit on which you can write class name, its responsibilities, and its collaborators, and also you can talk of the collaborations for which you want the collaborators. So if you design such classes, so this idea was initially projected as an idea to as a method to teach novices, to teach about object oriented thinking, how to think object oriented. So when you break down a system into objects, you can use these CRC cards and you can break down a system into many classes. You can give one card to each team of say 2 members, and they design these classes through they give the class a name, they talk about its responsibilities, and they also identify the collaborators of a given class and the collaborations. So every team is designing individual a single class, and then all these classes are working together, because every team also identifies collaborators, and over few iterations the system could get designed. So when you look at a system, it consists of many such classes, and they collaborate with each other, and then once you identify these classes, you can go on to further detailing of each classes. So the contributions of CRC are that the authors found that CRC gives a perspective of objectness in the problem domain. It's a good technique to teach object-oriented decomposition to novices. And a card could be of 4 by 6 inch size. This is a nice technique which can be practiced in classrooms. I often use this technique and ask the students and break the class into many teams and take a problem, and then an individual team can design a single class at interface level, mainly the responsibilities. At this time, you don't think of implementation, lower level implement the code, actual code, but you are mainly looking at the interface of the classes and trying to find out what are the collaborators, and over a few iterations the system gets refined and refined. Now we will take a look at an interesting method of designing classes, or even this can be also applied at system level. But now we are going to look at mainly class level design. So this is Bertrand Meyer's design by contract. So this is a very interesting method, and Meyer's contributions are that he discussed this method and provided this through a programming language support in Eiffel. Eiffel is a good programming language, and it was designed from software engineering point of view. So this design by contract can be applied even at implementation level through Eiffel, and the Eiffel can also be used to describe it at higher levels, and then seamlessly you can migrate towards implementation from design. So what is this design by contract method? What are contracts? Contract is a very important concept in object orientation. When we look at the interface is guaranteeing some contract to its users. Contract is always between two parties, the supplier and the consumer. The consumers are callers, or they call member functions on a given class, and the supplier is the class. So in a contract there are preconditions. If you provide these resources, I will guarantee something. So preconditions are to be guaranteed by the consumer, and post conditions are to be provided, are to be guaranteed by the supplier. So the contract can be mainly expressed in terms of preconditions and post conditions, and then now we will see how to design classes from this contracts point of view. So we are just listing here that preconditions are fulfilled by the caller. Class benefits from not having to check against preconditions. Now you can say that in order to invoke a member function on the class, its parameters must satisfy these conditions. If they don't satisfy, we will not invoke, we will not actually dispatch the method on the classes, on an instance of that class, whichever has been selected for invocation. So the implementation or the class benefits from not having to check against these preconditions. The supplier benefits from preconditions, and preconditions are to be guaranteed by the consumer or the caller in this case, and post conditions are to be fulfilled by the class. They are to be guaranteed by the class. And who is the beneficiary? Who benefits? The caller benefits from the post conditions, from the guarantees given by the post condition. The operation is completed, and the post conditions provide, or they specify what are the guarantees given after the operation is completed. So unless the precondition is satisfied, the member function is not dispatched to a method on the selected object. If a member function is dispatched, the code doesn't have to check against the parameters, because the preconditions would have taken care of it. In that case, the code is the core functional logic. We directly operate on the local state and complete the implementation of the method selected, and after that the post conditions are guaranteed by the class, and they are specified by the post conditions clauses. So we will look at an example contract for a class book. and we will pick up a member function called issue. So, you can issue a book to a given user, user is a parameter. So, what are the preconditions? The user must have a valid token, otherwise we will not complete the issue method, will not issue the book. So, user must have a valid token, and the book is not issued already, then this method can be dispatched, and the book is not marked as non-issuable, this is also precondition. If these are satisfied, then issue actual core business logic of this issue method can be dispatched. So, these constraints which must be satisfied before the member function is invoked are called preconditions. And then you have post conditions, which are the guarantees given by this member function after it is dispatched and completed, that the book is issued to the user. So, unless the preconditions are satisfied, this method is not dispatched, issue is not done, otherwise it is directly returned to the caller on failure of any of these preconditions. And if it is accepted, then the post condition is guaranteed. If it is accepted, the preconditions are acceptable, then the supplier must guarantee the contract to the consumer. If the preconditions are not acceptable, then the supplier should not undertake the contract, should not undertake implementation of the contract. So, this is a concept which you see in real life. Now, the same is also applicable in design of software entities, and Bertrand Meyer thought about this, and he has written a few articles, and in the book in his books on software development, object oriented software development, and also the book on IIFL, you can see more description and more examples and the actual programming language constructs for describing these contracts and then seamlessly moving them on to implementations. So, a language may provide support for contract specification. For example, IIFL provides direct support. If there is no support in the language for contracts, then you can use assertions in your programs. On paper, you can first design the classes and you can then map that to implementations using assertions. If there is no support for assertions in the programming language, then you write explicitly, you write that code explicitly and separate it from the business logic. It will be in the same member function code, but you will mark them separately, so that it is easy for the designer first to provide the precondition post condition code, and the implementation can actually implement the code. And if the preconditions are not satisfied, exceptions can be thrown. If the post conditions are not satisfied, it means that the implementation could be buggy. So, if the precondition is not fulfilled, exceptions are thrown. So, this was an important method, and it can be used at class levels, design by contract. So, this is one example, contract specification. For example, insert method on a set, insert text an item, and you could provide the preconditions. This is similar to IIFL. You can describe the precondition clause as, say, it requires, the require keyword is used to specify preconditions. The count is less than capacity, and item is not in the object in the set, it does not has X, and then the actual implementation code can be specified. When you are designing, this implementation code is not provided. When you are implementing, this code can be stuffed. The preconditions and post conditions described by ensure clause, that it ensures that it has X and count is equal to old count plus 1. So, this can be directly used in the implementation. The class can be compiled without the code first. When you design your design, you just translate into this template of contracts for every member function, and then when the implementer implements this class, which is designed using design by contract, he stuffs in the implementation there, and the exceptions etc. can be thrown by the programming language. And if you do not have the support in the language, use alternative constructs, which I had described a few minutes ago. So, class design involves exported member functions and interface as public compartment, implementations for specifying for the specifying class only, and implementations for the specifying class and for its subclasses. So, we had looked at, till now we looked at the exported member functions and the interface, which is public compartment. The design, and we looked at the design by contract, and we looked at the CRC method of decomposing classes and looking at the responsibilities of the classes and the collaborators. And then other two important aspects in class design when you want to detail or when you want to give the design of the implementations before the actual code is written, the implementation for the given class and implementations for the specifying the given class and for its subclasses. So when you are designing a class, there are two kinds of implementation again. One is for the methods of the class itself, and other part of implementation can be used by the subclasses of the given class. So we have these private methods and protected methods, or private attributes also and protected attributes also. So private and protected give you two kinds of implementation. One is for the specifying class only, that is private, and other is for the specifying class as well as for its subclasses. And the public compartment is the interface which is accessible for the external environment for the callers of the class. So that summarized class level designs. Now we will look at another aspect of class design, which is part whole hierarchy. So you could have objects inside objects. So when you are designing classes, you have to take into account this partology or breakup of class into many parts. So this picture summarizes what we are going to talk about. So you have objects inside objects, and when you have such entities, you can describe them using classes. So there has been a lot of discussion in literature about this part whole hierarchies and the part whole relation as such. But we will look at one specific description given by Odell. So Odell applied these criteria to classify different kinds of part whole relations. There are many kinds of part whole relations. For example, we can say that I am part of such and such department, or I am part of Speak Mackay or whatever this such and such organization, or you can say that LAMP is part of a projector. So when one uses this keyword called part of, say I am part of this country, or this a state is part of a country, or the first hour part of a concert, or the first 10 minutes which are part of a given lecture, the last 5 minutes which are part of a given lecture, what do you do? So we are using these part whole relation, where we are using this term called part of, but there are different kinds of part of relations, and then there are consequences on the design and the implementation, how you represent them in your design and how you implement them. What are the semantics of a given part whole relation? When you delete the whole, are all the parts deleted? When you invoke a method on a whole, is that method also dispatched onto all its parts? So these are various consequences. So you have to find out what kind of part whole relation are you trying to design, and then if you represent it properly, then you will be able to seamlessly implement it. If you have a powerful notation to describe all different kinds of part whole relations. So Odell described different kinds of part whole relations through these three parameters. First is configuration, whether parts have functional or structural relationship with the whole. Say I have a bag, in that bag there are many items. Now it is just a collection, and the items may not have any relation amongst themselves. But if you have car and its parts, the parts are related, they depend on each other, their input outputs are connected. So configuration is one important parameter to distinguish, which can be used to distinguish different part whole relations. Another property is homeomeris, whether parts are of the same kind as that of the whole. You take slice of a bread, the slice has the same the properties of the bread, but it is a part of the whole bread. And then another property is invariance, whether parts can be separated from the whole, whether they can be taken out. So these are important parameters which can be used to differentiate or to distinguish between different kinds of part whole relations. So he described different kinds of part whole relations. 6 kinds we will look at here, but researchers have found many different kinds, but say UML mainly give you two variations of part whole. You can capture them using aggregation and composition. But now we will look at these 6 different kinds of part whole relation to just give you an overview of how part whole relation can be used in class level designs. So, component integral object, it defines configuration of parts within a whole. So, for example, wheels are part of a cart, or bristles part of a toothbrush, or seams part of a film. So, since they have a sequence, so the configuration, it has a structure, the wheels are at a particular place, the configuration is important, the bristles part of toothbrush, it's the configuration is important of the bristles in the toothbrush. Another example is material object, made of, it describes invariant configuration of parts within a whole. Car is partly iron, it's invariant because you cannot take out iron from the car. Bread is partly flour, you cannot take out flour from the bread. Kheer is partly milk, if you take out milk from the kheer, kheer is no more kheer. So, material, this is material object, made of relation. Then you have portion object, defines a homeomeric configuration of parts within a whole. Parts are also like the whole. So, when you say you have a homeomeric configuration, how will you translate it into your class? If you have classes where there is homeomeric configuration, you are going to use inheritance over there. Slice of a bread, slice is also, it also has similar properties as that of bread. Meter part of a kilometer, a given meter part of a given kilometer. Then you have place area relation, homeomeric and invariant configuration of parts within a whole. Powai part of Bombay, or Everest part of Himalayas, or boundary line part of cricket field. So, we are talking about a place and an area. You cannot remove the place from the area, you cannot separate it out. Then you have member bunch relation, where it defines a collection of parts as a whole. Tree is a part of forest, employee is a part of a forum, ship is part of a fleet, or a person is part of an organization, or is a member of a given club. So, member of relation is a different relation, and there is a slightly different member of relation where the members are related to each other, you cannot take out the members. Defines an invariant collection of parts as a whole. Laurel part of Laurel and Hardy, or Puriya is a partner in Puriya Dhanashri. This is a classical Hindustani raga where you cannot, if you take out one, then the rag breaks down. So, the members in the member partner, they are also related to each other, and it's an invariant collection of parts in a whole. And then what are non-aggregation relation? Topological inclusion. For example, customer is in the store. If you have such a requirement, then you cannot design for a part whole relation. Meeting is in the noon. Classification inclusion. Ramayana is a book, or UML is a modeling notation. This is not part whole. So, this is classification. Attribution. Weight of the box is 50 kg. Or attachment. Earrings are attached to the ear. So, this is mainly attachment or association. Ownership. Bicycle is owned by Subhash. Ownership is not part whole. Bicycle is not part of Subhash. So, these are different relations which sometimes might get confused for part whole relation. So, when one decomposes a given class into part whole, then we have to exclude some non-part whole relations. Then there is an important aspect in part whole relation called transitivity. A relates to B and B relates to C. Does A relate to C? For example, car, engine, piston. Engine is part of car, piston is part of engine. So, piston is also part of car. Then you can say Bob is part of maths class and Bob's arm is part of Bob. So, is Bob's arm part of maths class? So, if you apply this criteria, that if you find out these kinds of different kinds of relations, now maths and Bob, there is one kind of part whole relation, Bob and Bob's arm, there is different kind of part whole relation. So, if that is the case, then transitivity will not apply. So, when you are designing your classes, the same is also applicable. Say for example, if you have compositional objects, so you have document hierarchy, now the leaf documents or the composite documents are also documents, and the composites aggregator, they are the whole for many internal documents. Then the operations that you invoke on the high level composites are also they can be propagated to the lower level classes, and the transitivity applies. For example, rotate, if you rotate a shape, all its components are also rotated internally. If you move it, all the components are moved. If you delete the high level shape, then the lower internal shapes are also deleted if you have a group. So UML gives you this notation for capturing mainly two kinds of part hole relationship. One is called aggregation, another is called composition. So one is the top one is shown with a hollow diamond, it's white color, so it's you can see that it's a hollow diamond, and the bottom one is a filled diamond, it's a dark filled diamond. So you replace this by black color. If you have a black and white picture, then the distinction will be clear. So when you are in doubt whether it's a part hole relation where it's a stronger relation where there is propagation of member functions, then you are going to use composition, otherwise you can use aggregation. In aggregation, the part hole is little bit weaker. So if you are having relations like member hole, or A is a member of B, if you do not know whether there is strictly very configurational properties amongst the parts, and they are all required for the functionality of the whole component. If you do not have a component integral object, if you do not have a stronger part hole relation, then you can go for a weaker part hole relationship. So you can say one is a weaker, another is a stronger part hole relationship. So these are the mainly two categories which are recognized by UML modeling notation. So in this way we can use our part hole relations and design the part hole hierarchies of classes. Now we will look at another aspect of class level design, that is inheritance. So we first saw individual classes, we looked at the CRC method, we then looked at the design by contract method and how to design the classes from preconditions, postconditions point of view, from contracts point of view. Then we looked at how to break classes into part hole, or what are the different kinds of part hole relationship. Now we will look at this inheritance relation, which is also very important relation in class level design. How to design new subclasses from old. So what are the different kinds of uses of inheritance in subclasses? How do subclasses use inheritance? If we first look at these different kinds of uses of inheritance, then we will be apply these different kinds to our different class level design requirements. So you can use subclasses as pure extensions to superclasses. You can add new attributes, you can add new member functions. So your superclasses may be concrete classes, which we had described earlier, and you can then add new attributes and new member functions to those superclasses. Or you can use subclasses as full implementations. So this is applicable when you have a pure abstract class as a superclass. And thirdly, you could use subclasses as partial implementations. This is applicable when your superclasses are partially implemented. So they are partly concrete, partly abstract. These are again, the applications are the same. The pure extensions can be used where you have, say, pure concrete library classes. Full implementations have to be used when you have inheritance hierarchies with abstract classes, or they are also called interfaces, mainly in component technologies. And you can use subclasses as partial implementers in frameworks. So mainly those three kinds of inheritance, or these three kinds of subclasses, can be used in class level designs with inheritance. So inheritance for pure extension, inheritance for full implementation, and inheritance for partial implementation. These can be used. There is one aspect of inheritance which I have not listed here, but which is also sometimes used. That is called mixins. Use inheritance to actually represent part whole. So you have an object has many parts, and the parts can be used as classes. And in this case, The whole is the subclass which uses inheritance, and using inheritance all the instances, one instance of each of those superclasses become part of the object or the memory map of the object of the subclass. This is called mixin. But in this case, one has to remember that the abstraction of the superclasses is not exported by the subclass. That means the inheritance cannot be public inheritance. So the fact that the subclass is using the superclasses as parts only should be reflected in our implementation through private inheritance. And you have to also note this in your design, that you are designing your hierarchy or you are designing your subclass as a mixin. So inheritance has to be private in such a case. If the parts which are modeled as superclasses have a different abstraction that of the whole. So these are various important aspects of inheritance. So we are not going to go into much details of inheritance and then the implementation levels, because we are only mainly focusing on the design aspects. So after the inheritance aspect, we will now go on to components. So now we explored various aspects of class level designs, individual classes, design by contract, part-to relation, CRC, and inheritance, aspects of inheritance. How do you design your subclasses? Now we look at components. So what are components? How are they different from classes? So compare this term with components in real systems. What happens to components in real systems? For example, you have a circuit board, you have a circuit, and there are many components. You can remove a component, you can plug another component which is of the same kind, then the circuit will work. So in a given context, a particular entity can be a component. So context is very important. For example, components in single address space within a process, dynamically linked libraries. When the process is executing, you can change the implement, you can change DLL and you can then read it in. So DLL is a component in a single address space. Or if you talk of components in distributed systems, then you could have examples in Corba, Java RMI, DCOM, and so on. Then your context might need that your entities must be component in an interoperable system. For example, I have a component which is implemented in C++ and it works in a system where there are other languages like Java, FL, and so on. Will these components implemented in different languages be able to communicate with each other? And then that is called interoperability, because there is communication amongst heterogeneous environments. So your component, when you talk of this term called component, your components are components in a given context. And what is that context? That is very important. So now we will focus on this component. We will look at the details of what exactly is a component, so how it's different from a class. So when we talk of components, when we design components, we mainly focus on the interfaces of the component, and the implementation can be in any given language or in a given context. So interface is very important for the component. So when we talk of component orientation, you think of interfaces first. So class as a term is very close to, firstly, class provides you separation of interface and implementation, and component is a concept where you are talking of changeability, when you are talking of removing something and placing something else there. So that aspect is very important. So component is very heavily used term in technological context or in implementation context. So when you are when you are designing your components, you first look at interface specification, and when you are implementing them, you are looking at then the programming language choice and so on. So component systems such as Corba give you an interface specification language called interface description language, IDL. Using the IDL you can define these interfaces of your components, and then you have to use tools to map this interface into an implementer, and then into the implementer you have to plug the implementation. So these are the three main steps. So when you design the components, you first think of the interface, and then when you want to implement the interface, when you want to provide the components implementation, then you map this interface into the implementer, which is mainly a skeleton in a given language. So you might say that you have an account component which has the interface, deposit, withdraw, balance, and so on, and now you want to implement the component in C++, in Java, in IFL. You can implement it in any language, and the client implemented in any of these languages will be able to invoke these member functions on your component in spite of its in spite of you implementing the component in a different programming language, because you are thinking of the component from the interface point of view. So standardization is very important in component orientation, in today's component technology. The interface description language has to be used. So different component technologies are there in existence, and they have different interface description languages, and you describe them and then implement the component through the given implementer generated by the tool. It can also be generated by hand, but the tools are available with almost all technologies which can generate the skeletons from a given description, and then in the skeleton you can plug implementation. The implementations can be provided through different mechanisms such as inheritance or delegation and so on, but we are not going to look at implementation aspects. So at design level you are mainly focusing on interfaces of the components, and we know that components can be implemented in different languages, and in a context where interoperability is important, mechanisms are provided by the component platforms or the component technologies for the interoperability aspect. The other decisions about components non-functional properties, about the components non-functional properties. So these are also to be taken into account when you design components. What are the activation policies? How do you start the components? Is the component started? So when I use this term start the component, we are talking of actually instantiating or actually making the component active, so that it can execute a given request. It can execute the code against a given request. So what are the activation policies? Is it started every time a member function is invoked and then brought down as soon as the function is completed, or is it started once and then shut down by the end of the day? So what are the different activation policies? So you have to design for the activation policies of a component. Registration and discovery. In a distributed system, when there is an object which is available in the distributed network, in the network of machines which are distributed, you need this registry and you need the ability of discovery, so that clients can discover these remote objects through these registries and then invoke them. So if component programming is made available for an object oriented environment, you can use them as objects. Therefore I am using this term called object in a distributed environment. So you will come across this term called distributed objects. So this term is also used to refer to component programming in a distributed environment using object oriented programming languages. For example, in Corba you can use C++, Java, IFL, Smalltalk, and interoperate. So these are the object oriented programming languages which you can use in Corba. You have Java environment for making available this distributed object platform in Java, and you also have similar technologies in Microsoft platform. For example, you have comdcom.net. So these are some of the major component programming platforms, and they also make possible this distributed object programming. And components are the component orientation is also possible in object oriented domain in a distributed environment. Then, so we're talking of registration and discovery. This is an important decision one has to make. How many registries you are going to have, how are you going to organize your components. Location and implementation, where are they located, where is the implementation located. This is sometimes closely related to activation policy. Then you have other decisions such as concurrency within a component and synchronization within methods, amongst the methods of a given component. Say you may want to lock a component when you are in the midst of a method. Persistence of the component, is the state persistent? When you bring down the component, will the state be stored? When you bring down the machine, is the component still persistent? So these are some of the design decisions which one has to make when you design components. And then how do you reuse components? So we had seen inheritance relation in object technologies. When you talk of components, since we are decoupling interface from implementation, we are saying that interface can be in one language, interface description language, and implementation in a different programming language. You can reuse these two separately. You can reuse interfaces using inheritance and describe new component interfaces using old component interfaces, and you can reuse component implementations using implementation specific reuse mechanisms. If you have a C++ implementation for a component description, you can use inheritance, you can use composition or aggregation, and so on. So reuse can be applied at interface level separately, implementation level separately. This is about component oriented design, or when you are designing component systems. So we looked at now as a summary, we had seen class level designs, we had seen individual classes, we had seen what are the different compartments in a class. Then we had seen the method of design, the CRC method. We had seen design by contract. Then we also looked at part-whole relation. We looked at inheritance, different kinds of inheritance, how to design subclasses. Then we looked at components, what are components, how they are different from classes, how do you design the components. Interface is what is very important in components. And then we looked at how you reuse components, you reuse interfaces separately, implementations separately.